Hello and welcome for another set of I Know Nothing in Cosmology, and today we're going to be looking at special relativity, which is, in my opinion, way easier than Newtonian physics. Okay, so here we go. The principle of relativity quite plainly states that as long as motion is uniform, meaning moving at a constant speed in the same direction, velocity, time is no longer perceived, and by that I mean no longer perceived in the way that you usually perceive it. This applies to observers moving at or greater than the speed of light. Fun fact, space itself moves faster than the speed of light, and I'll cover that in another review in more depth, but it basically means that space was expanding so far out before the so-called Big Bang that light has not caught up. Light itself is both a wave and a particle. Many particles, if not all particles, have this wave-particle duality to them, meaning that they can act like objects or act like a wave, particularly with light, and so meaning that particles act much like a wave due to the uncertainty principle, which states that no one can know for certain where or when a particle will travel, so its velocity or its placement cannot be known simultaneously. That's why their movement is like a wave. And light speed and its particle constituents is constant and unchanging no matter which medium it passes through. And another fun fact, photons have a zero spin, angular momentum, and zero mass, which is why they're so fast. Briefly, I want to talk about the electromagnetic scale or electromagnetism, which was discovered by Clerk Maxwell. It's basically the behavior of electric and magnetic fields, which are actually two sides, I apologize for that typo, two sides of the same coin, so they are one and the same, they just act differently. They're produced by static charges and flowing charges known as currents. Magnetism is the measurement and attraction of charge, and electric charge is the exchange of energy. So oscillating and vibrating electric fields and magnetic fields work in conjunction with one another. Light in particular, its colors comes in several wavelengths relative to its source. So radio waves, for example, interact with photons and produce a tangible, measurable wavelength. So as much as light is constant through whichever medium, whatever medium it interacts with does produce its own form of response to light. So as you can see here, the lower something is, it's going to be red. The higher something is, it's going to be blue. And this has a lot to do with the way these fields interact. Wavelength, frequency, and light. This is an equation. Wavelength is this curious symbol here. I don't know the exact name for it. Frequency is F, and C is speed of light. And so frequency is this curious symbol over light. And basically this means that the frequency of a wavelength is consistent to it divided by the speed of light. So electromagnetic waves are characterized by wavelength, frequency, and number of waves, which I'll go into here. Each photon, considering that light is composed of photons, is electrically neutral and has a measurable energy and momentum. So its wavelength is like this. So these are up and down, up and down. And here's a good example. A high note has a shorter frequency, much like this. It doesn't mean that the sound lasts any longer. It just means that the energy within that wave is more compact, and thus the two waves are going to take a shorter time oscillating between up and down, up and down, up and down waves, whereas a low note, for example, will have a longer frequency. It will take longer in that short span for those waves to go up and down. And this is one way that voice matching material or technology works, is by matching these frequencies to a person's voice. So it's kind of like pitch. It is pitch, basically, just put into a more dense terminology. And then, of course, we have simultaneous experience. Events occurring at the same time have no meaning in time. Not absolutely. It all depends on the motion of the observer. So if you travel at the speed of light, depending on the motion in which you're traveling, your experience of time result in a different experience of events. And I'm going to quote this book that I didn't mention in my initial review to introduce these topics. But if a planet that orbits, oh, I'm sorry, I said orbits when I should have said revolves. So it's daily revolution of a planet that has a daily revolution faster than that of Earth will actually experience a slowing of time. So whereas its orbit around its sun may be a year like ours, if its daily revolution is faster, um, time is slower, such as time can bend space. Force that mimics mass, from what I've deduced, can bend space time. And since light can bend and thus directly affects the experience of times and events, so that's a lot to swallow. So basically, what I'm getting from this, and I'm no expert, is that when you are traveling closer to the speed of light in a constant momentum, in a constant direction, so for example, uniform acceleration, like in a circle, and you keep moving and moving and moving and moving, although I shouldn't say acceleration because acceleration means that velocity is increasing, but a uniform velocity, I'll say that. And if your planet is going faster than Earth's daily rotation goes, then because that speed has the capacity to potentially bend the way light works, your experience of time, because you need light to perceive things in this world, becomes time is much slower. Now, I do not believe this means the days are longer, because evidently if your planet's rotating faster, you're going to experience like probably an 18-hour day, for example. But your time, for example, you are going to feel that time has slowed down. I can go into this much later, especially regarding black holes, because the gravity is so intense and light gets trapped in it. Again, we're dealing with light here. Time can actually slow down. So think of gravity and light as being loosely fused to the same side of the coin for now. So motion, speed, and light all correspond to how time is perceived. So, real life experiments of time, and these are two in particular from two of Brian Greene's books, or maybe just this one. He does repeat himself sometimes, so it's quite possible it's two or one book. But they're both from the books that I have quoted in the introductory video. In order to prove that time is relative to speed, here on Earth, by the way, this wasn't done in space, we do not have the technology to put a person at the speed of light without killing them. Clocks were wound to sync accordingly together and were placed upon various high-speed jets to travel at particular speeds, some even breaking the sound barrier. When the clocks were studied after that experiment, the clocks traveling at faster speeds were slower than the control clock based on Earth's relative experience of time. And in particle accelerators, for example, the closer a muon, an archaic, heavy, short-living particle, because when particles are heavier, they tend to die faster, travels or is given enough energy to travel at the speed of light, its lifespan is actually longer. Its aging slows. So in order to travel through time, one has to somehow use light, or if you want to be really extreme, gravity. So the speed of light is relative to time. And I also put in here, maybe gravity is too, considering it's theorized that gravity has a zero mass, just as a photon does. And as I stated previously, the heavier a particle is, the more likely it is to die. So this is kind of interesting. These are some parallels I noticed in my studies, and I'll definitely get into this in more reviews, but I just think it's fascinating. Time dilation. Muons and clocks aren't the only things that can experience a slowing of time. How is time measured in a mathematical sense? And we particularly need math because our technology thinks mathematically. I've taken coding classes. It's a pain in the ass, trust me, trying to get a machine to think as we do, but on mathematical terms, or very forward 90-degree angle, 120-degree angle. It's insane. So time by zero is equal to twice the diagonal distance over the speed of light. I want to say that this is diagonal because I would definitely consider warping of space, because if gravity can warp space, can light also warp space? I honestly don't know. I would think of it as going across something instead of going directly to, but that's just my opinion. And of course, we have to consider the wavelength. Oh, I apologize that this copied way more than it should have. I thought I deleted it. Apparently not. Wavelength relativistic factor. So time equals the Lorentz factor. An inverse variable. Time travels in proportion to direction and speed by time zero. And the reason time is zero is because our perception of time at that speed will be going so fast that it will feel like 0 per second. So that's the Lorentz factor. This is the Lorentz factor right here as well. So y equals 1 over square root of 1 minus velocity squared minus speed of light squared. And like I said, particularly with inverse variables, it does correlate that relationship. So that's why time over the Lorentz factor by time 0 is very important, because we have to connect that our ability to travel per this time is going to come out possibly to a negative factor, because its length for us, if we're observing some moving at the speed of light, is so fast we cannot put it into observable terms. And that when you typically, as I said, if we have something in the negatives, because it cannot be observed by a mundane measurable means. And again, I know nothing. This is only my personal take on what I'm reading, but it's fascinating and it's beautiful. Length contraction. I want to call this the warping of space, but I called it the warping of speed, particularly because speed is very important here. Perception of length by speed of constant velocity. Speed of light, remember, all's relative. So what I mean by this is that if you're moving at the speed of light, in comparison to how you would observe length, it would seem much shorter. Remember the planet analogy, where if the planet rotates faster, time is longer. However, where was I going with this? However, because time may appear longer to you, that doesn't mean objectively you're going in different lengths of things. Your perception of length by constant velocity differs. So this equation is length, object at rest, u, divided by 1, divided by the Lorentz factor, again, this number, which is 1 over square root of 1 minus velocity squared minus speed of light squared. And then, of course, Einstein's amazing equation, E equals mc squared. I can't seem to find the square factor on this laptop. I don't know what's wrong with it. So energy is mass times the speed of light times itself, which I think is just beautifully fascinating, especially if you consider things within the Big Bang, how dense it was, how fast particles were moving, how dense it was. It's so beautiful to imagine. Which also, incorporating light, on a flip side, in my opinion, it has to incorporate gravity, considering the parallels between light and gravity both dilating and having influences on time. So what does this say? It basically says we're in a 4-dimensional universe, as time is an all-pervading force, as in any of the 3 directions. So by geometry of space-time, every event is observed differently. Its energy and momentum, which momentum might include weight, depending on our definition, being observed and felt at different times. Remember, even the smallest hand can deliver the hardest punch depending on how much energy and momentum you put into it. And of course, the space-time interval, which always fascinated me when I started reading it. It locates time and light. So S is space-time, C is time of light, and T is time. X is object, and delta, this symbol here, in this equation, I kind of assumed it meant a change in velocity, which is direction, but it could also represent a change of quantity and everything. So thinking topologically, it has a form, a shape to it, an artistry to it. But what I see is that if I remove this part here with the x's, I'm just getting the space-time, I'm just getting speed and time and delta squared. So everything in space-time already exists, with or without the mass of an object. So I see secrets unfolding. It's relative to light, so is perception of experience, because we cannot experience things directly without light or interacting with the electromagnetic scale in some degree. Like, do you think when you touch your skin, you're touching your skin? No, you're actually touching the electrons, and you're interfacing with that, which is so cool. And that's why delta is so important. It's relative, because our perception of time is different, and the speed of light is going to be very important to our perception of time. The faster we move, time will slow. So yeah, I think that's about it. Yeah, that's my last slide. That was a much shorter review than I thought, but I simply adore this idea. Like, I can't get into how wonderful it is.